Okay, so let's start today with the second part, basically to catch you up with the past lecture. The setup of our problem is that we are given a Hamiltonian. That Hamiltonian is going to be sparse, D sparse. That means that in every row we have as much D non-zero elements. We are going to call the indices of the rows as J, the indices of the columns as K, and L is going to be the index that is going to give you the cardinality of the non-sparse elements. So basically, we are going to suppose that we have oracular access to this Hamiltonian. So basically, given a row and a value of the index of sparsity from 1 to D, this is going to return us the column in which this non-zero element is. And basically, once that we provide the second oracle when with the index of a column and a row, it's going to return us the value of that element in that position, in that coordinates. And given these two oracles, we saw that we were able to build these two operators efficiently with a polynomial number of gates and calls to these oracles. This is the operator related to the quantum random walk, to a step of the quantum random walk. And this is an isometry also needed to define the quantum random walk. So basically, we saw that taking an initial state of the form, okay, this was we applied two evolutions. First, we applied the isometry. We got something intermediate. I'm not going to write it down. And then we applied the quantum random walk. And just a reminder, this isometry is basically amplifying the Hilbert space. So we got something in an enlarged Hilbert space. Just a reminder, the action of T is the following. When we apply T to an eigenstate of the the Hamiltonian can be written as the sum of lambda. So this is the eigenbasis of the Hamiltonian. So when the isometry is acting on this is going to map it to a superposition of two eigenstates of the quantum random walk operator. So basically, after applying the isometry to this, we are enlarging our Hilbert space, and we are going into a superposition of two eigenstates of this operator here. So basically, we have that this is an eigenstate, so the eigenvalue, let's call it lambda plus, and the same for lambda minus. So basically, the thing is that when we apply to this superposition the quantum random walk, as we have that these are eigenstates, we have the following final state, which is our initial starting point for the lesson of today. So basically, the state that we obtain, I'm going to write it down because it's quite important, is going to be the exponential of I arcsine of lambda it is max d lambda plus let's call this lambda tilde plus pi. Okay, and lambda minus. So the previous lecture we saw how to get this quantum state, and if we were able to get the same phase for both eigenstates, we may apply the inverse of the isometry. So we will basically recovering something that could be like exponential of arcsine of lambda lambda. Because basically if we have superposition with the same phase for both eigenstates, when applying this, we'll obtain that.
Can you do a super fast reminder of what was T and why has it enlarged?
Yeah, okay. Yeah, basically, just to catch you up with this, to understand the quantum random walk, basically what we do, it is suppose that every row of the Hamiltonian is going to give you a kind of pseudo probability of transitioning from node G to node K. And basically, the thing is that to encode these dynamics into Hamiltonian, of the Hamiltonian into a quantum state, what we do, it is basically to take the computational basis eigenstates in which we are describing our Hamiltonian, and we are going to map this state to an enlarged state that basically in the second Hilbert space is going to encode a superposition of all the states to which this can move to, and basically here we're going to have like a kind of like a transition probability. So this is what we call phi j. So basically, given a state, we are going to enlarge a Hilbert space. So in the second Hilbert space, we are encoding those states to which the initial state can evolve to. So basically that's the idea, that we are going to encode a superposition of all the possible initial states and a distribution on all these states, and we are enlarging them by encoding this. So this is why it's an isometry, and actually the key thing to prepare this is to be able to prepare this isometry, and to prepare this isometry, that's enough with knowing how to prepare from J the state 5J. So this is a little bit tricky, but can be efficiently done with these two oracles. No? S is the swap weight. Okay. The V. This is like two operations. So to understand what a quantum random walk is, in a quantum sense, you have to imagine that initially you have a certain distribution on the superposition of states, and you are going to evolve this through a unitary. So basically, this unitary is going to have like a transition probability between eigenstates of the superposition given by the entries of the Hamiltonian. Cannot be exactly that, because what we do, that is why we have here the norm 1 of the Hamiltonian, it's basically are going to compute the sum of the absolute value per every row. So basically that's going to be the norm 1, and we are going to normalize with that norm. So we will have this row may not sum up to 1, and we have like some extra probability that we are going to encode in some ancilla. But in the end, from this Hamiltonian, the operation that is going to basically evolve according to this probability of transition is going to be given by this quantum random walk operator. And this quantum random walk operator needs from this isometry. And this isometry basically is encoding everything together into an enlarged Hilbert space, and to evolve one step and basically transferring the states from J to K according to the probabilities given, you need to do these two operations. And these two operations are given by a reflection about this state for every J. It's a conditional reflection, because given a J, you have the state from which you have to do the reflection and then the swap. And the thing is that when you compute the expected value of when you compute this expected value, which is phi j if I remember properly. I think it's kind of this. So when you compute the expected value of this, the values that you are going to obtain are going to be proportional to the Hamiltonian. So basically, this operator is intuitively creating a unitary that has probabilities of transition that are proportional to the entries of the Hamiltonian. It's not that easy, but okay, this is not the main focus of this, but okay, whatever. So the thing is that you have to believe that this can be done efficiently. The details are more tricky, but let's go through what it's the aim of this talk today. So basically, we have been able to create this state, and we have several problems here. We have that the spectra of the Hamiltonian has been modified because we have the arcsine function here. That's the first problem. It's not linear. Maybe we could linearize the spectrum of the Hamiltonian if we had like a first order approximation or something. That's the first issue. And the second issue is the sign problem. Because actually this pi here can be seen as a -1 here, and we have a different sign for the two faces. And we have to correct this somehow. Several proposals before have used different methods to manipulate the faces of these two states. And these methods rely on quantum phase estimation or linear combination of unitaries. But all of these methods were obtaining complexities that were not scaling optimally until the following method was proposed. And the method that I'm talking to you today, it is the quantum signal processing. So basically, we're going to apply a transformation on the phases of the two eigenstates, and the transformation that we wish to apply is basically, okay, let's say we have a transformation h of theta with theta the phases, and we want this to be the evolution time times the norm of the Hamiltonian times the sine of theta. So basically, if we were able to apply this transformation to the phases, when we apply this transformation to the first one, we are going to obtain lambda. That's the result of applying the transformation. So we are going to have this phase here. And for the second one, it's exactly the same, because if you remember, if you apply this property, I think it's a plus b. This is kind of like sine of a cosine of b plus cosine of a sine of b. Oh. So basically, sine of pi is 0 and cosine of pi is -1. So we are going to cancel this minus, and tada, we are going to have the same phases for both. So we are going to have the exponential of the Hamiltonian, and basically, if we are able to apply this transformation, the state after this transformation is going to be minus or plus 1. Actually, I can add a minus here. So it's going to be lambda t, and we are going to have lambda plus lambda minus over 2, and then I think it's square root. And then we can basically compute the inverse of the isometry with this, and we are back at home, because we will have kind of this with the t dagger, t minus 1. Okay, so that's the plan, and the thing is that how can we manipulate the phases of a given quantum state? This is what I want to show you today. How can we transform this amplitude via quantum control techniques, and what kind of transformations can be done? So basically, this is our starting point, and this is a transformation that we want to carry out. Okay, let me erase this. That's what we are going to do. So this is quantum signal processing, and the most amazing thing about this technique is that only needs a single ancillary qubit. And basically, the transformation is going to be encoded into the ancilla. So let's go with this.
But what is the changes that you are making? Here are data and you make some changes.
So
What are you making those things data?
if I apply to these phases this transformation, so in this case theta will be,
Theta to h theta.
yeah, in this case theta will be arc sine of lambda norm of the Hamiltonian d. So if I calculate h of theta according to this transformation, this is going to be minus lambda t. So that's basically what we want to do, transform these phases, this phase to this other phase. Okay. So I'm going to write down all the details, so do not worry about it. So basically, the problem here is that we want to linearize the arc cosine up to the sine problem. So basically, let me begin with some quantum control techniques. Quantum signal processing. I'm always confused with writing this well, but never mind. Maybe it's two C's, I am not sure, whatever. So our main tool are going to be these rotations. So basically, we are going to be able to rotate around an arbitrary axis and with an arbitrary angle, and this rotation is going to be described as cosine of theta plus sigma y sine of theta. So basically, this is a single qubit rotation. You know, this is one of the things that can be perfectly controlled on single qubits. So feel free to say that this can be perfectly implemented, and there's no problem to do this operation. So the idea behind of this, it is that, okay, let's take a single qubit in an arbitrary state, for instance, take it in the initial state to be 0, and if I, for instance, apply a sequence of these rotations, and taking, for instance, the rotation axis to be the x-axis, if I take p over 2, and I apply n of these gates with a rotation of theta on the initial state 0, and then I properly project, for instance, into the state 1, I'm going to compute the function sine of theta over 2 into the amplitude of the quantum state. That's the idea, that with these rotations, I'm basically picking an arbitrary sequence of rotation axis. We are going to be able to choose an initial state, choose a sequence of rotations, and choose a final state, and we are going to be able to compute a function on the amplitude of the ancillary qubit. So, in general, we are going to have an arbitrary sequence of these gates. Inside the sign. Yeah, I apologize. Yeah. So the idea here it is that given a function of theta, this is going to be given by a sequence of rotations about arbitrary axis, and basically we have that's going to be a given function of theta, an arbitrary combination of rotations, and here the main thing is that we have a vector of rotations of angles which is going to determine the angle, the axis of the rotations, And this is what we will really need to calculate. So basically the first thing to note here, it is that because we are working with a single qubit, we can basically express this sequence of gates into a decomposition into the Pauli basis. So basically, rewriting this expression into the Pauli basis, we're going to have that all this sequence can be simply written with this decomposition here. Okay. So now the thing, it is the following one. How can we use this here to be able to reconstruct the operation that we want to implement? So basically, we want this to be roughly approximated the function that we want to implement into the phases. So that's the main thing of the protocol, that by choosing the initial state, the state in which I'm going to project, and the angles that are going to give me these functions on the different Pauli bases, I'm going to try to approximate the function onto the phases. So the really hard problem here, it is to find the sequence of angles that are going to give us these functions on the Pauli basis. So the problem here is finding the rotations. Yes?
Why do you fix the angle theta and when you transform into a vector also of different angles and the sequence?
That will be generalized quantum signal processing. But so far we are assuming that theta is the phase of the initial state. So that's something fixed. That's the argument of the function. That's the input. So basically, we want to compute a function of theta. And the way of computing an arbitrary function of theta, it is by changing the axis of the rotations.
But how do you make that the phase of the state you want to transform, which is theta, right?
Uh-huh.
How do you make it influence the gates you are applying? Because it's like you're saying, I am applying a chain of gates in which each gate, the operation it performs, it makes a rotation around phi with an angle theta, right? But theta is in the state you're trying to transform.
Yeah, I'm going.
It's like a control, not.
Yeah, it's a control. You need, yeah, I'm going to go to. But the first idea that I want to transmit you it is that given an input theta, it is possible to basically calculate a function of theta.
Okay, and that approximated equalities with the whole sum.
Or the whole sum. Actually, we're only going to use these two terms here, A and C, and that's going to be enough.
H is a function or is a matrix or it's...
H is a function of theta. In our case, H of theta is well, that's not, well, yeah, okay. The thing is that when it's more complicated because I need to implement this transformation, this set of rotations, and then I need to pick an initial state and a state to project. So when I pick all of this and project the ancilla, I'm going to get that transformation into the amplitude of the remaining state. So basically, you are going to have the state to which we want to transform the amplitude, and we are going to have an ancilla. And I'm going to do all of this sequence of rotations into the ancilla, and with the proper choice of the ancilla, and here we have the rotations. I don't know how to call of this sequence, whatever. This V theta. So yeah, basically let's say that we have ancilla for projection, we have b theta identity, and here we have ancilla initial value, and here we have the target state. So this is what is going to modify the phase of this state. Yeah. Control on the value of theta given by the initial amplitude of phi. Yeah, I haven't gone through these details yet, but yeah.
How can you put any information in the side state if you don't do any entangling operation?
Yeah, I'm going to explain it. I just wanted to give you the idea that forget about the control operation right now. So basically, if I have a single qubit and I pick the initial state and the final state in which I'm measuring, I can compute an arbitrary function of this with these Pauli rotations. Actually, one of the main problems is what functions are achievable with this combination of observables. Okay, so yeah, let's recap. So this is the first thing in quantum signal processing, that using these unitaries we can reconstruct functions. The following thing is our target operation. So okay, so basically now imagine that we have a certain unitary, and its unitary is going to be given by okay, so in our case that will be the unitary that implements this simulation here, and we want to calculate this new unitary. Do not confuse this notation with the one of the previous talk, please. So basically, we want to go from this to this. That is what we want to do. We want to apply this h function here. So I'm going to go through this with 3 steps. So first step. So the first step is what is called signal transduction. So basically, we are going to go from the initial unitary to this unitary. So this is acting on the initial state, and here we have enlarged our space, and we have added an ancilla. Actually, this unitary here can be written as the following. Well, oops. So, thank you. And here is this U0. So basically, we built first the rotation around the x-axis. So this is a control rotation actually per the value of the eigenstate, the theta associated to the eigenstate. And the thing is that we actually are adding an extra phase here. But we don't have to really worry about. And then to perform the rotation about an arbitrary axis, we are adding the angle into a second operation. In terms of a quantum circuit, the circuit that implements this, it's relatively easy. So imagine first register is ancilla, second register is initial state of interest. So basically, here we have the phi sigma 2. Then we have Halmar gate and control version of W, H, and like a minus? No, this is minus, okay. So basically, this here implements U0, and the other two are added to calculate U5. And who is W in our case? W is the sequence, it is the sequence of applying the quantum random walk operator this is our W, the sequence of the isometry, and then apply the quantum random walk operator, which is and this operation here, basically applied to the initial state, is going to create the arccosine of lambda tilde plus minus arccosine lambda tilde plus pi. So basically, W is doing this. Yeah, in our case, theta is this thing. So for the particular case of the quantum random walk, we know how to implement this W. And in the end, having a control version of W is as much controlling every gate. So it's not a really big deal. So first step, we have this operation. Second step. So, well, the thing is that every of these U5s is going to implement a rotation of angle phi on the ancillary qubit, on the axis defined by the angle phi, and of angle theta on the ancillary qubit. So basically, the thing is that we need to compose all of these rotations to obtain the function that we want to implement. And basically, this, well, it's confusing because I use the same notation, but this is the sequence of rotations that I presented before. So basically, the sequence of rotations are given by the sequence of unitaries. So the rotations that we did before with a single qubit now are done by this unitary. The tricky thing here to avoid this phase that arises here, it is that we can use this equality and basically we can erase this phase by applying an even number of rotations and sometimes rotating around this axis and sometimes adding the phase pi. So with this, we have applied the well, after this sequence of unitaries, what we have it is here that we have applied the A theta identity blah 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 on the ancilla. Actually, this is like condition on lambda, and here we may have like lambda. So basically, we have applied a condition function of lambda into the ancilla, and this is the sequence of rotations that I introduced before. So basically, for every eigenstate with eigenvalue, with a phase in the eigenvalue of theta lambda, I have implemented a rotation of a function of theta lambda into the amplitude of the ancilla. So we would like this to be the transformation that we want to do to every theta lambda. So here we still have tricky part, which is what is the state, the initial state of this ancilla, and what is the state that I have to use in this ancilla to project and calculate the proper function. So we need to define what is going to be the initial state of the ancilla and what is going to be the measurement state for that ancilla to obtain the function that we want to implement. Any questions? Okay, so basically the idea it is that the first thing that I told you, which is, okay, if we have a single qubit, we can apply this transformation into the amplitude of this first qubit. We have generalized that, so basically we have entangled this qubit with the initial state, which is our target, and we have performed a control rotation on this qubit depending on the state of the superposition. So basically, we are simultaneously working with all the possibilities of this angle theta, and for every of them, we have calculated a different rotation. So how can we apply this tool for particular case of transforming the arc sign into the sign, which is the key step here. So basically, we need to know which functions we can approximate with this sequence of rotations here. So here we have a theorem, and basically it says the following. For any real value of theta, we are free to choose any angle, such as both functions, the sum of the squares of both functions must be minor or equal 1. This is the first condition. The second condition is that A of 0 must be 1. And the third condition, it is that yeah, these are complex functions. Well, yeah, I mean, you can replace a square per this. Well, I think that, well, let's suppose that these are real functions. C of theta, real. And basically, we have to impose that this has a Fourier series. Remember, n is the number of rotations that we are doing. And the same for C, but with the odd series. So this is going to be, say, k sine of k theta. So if we choose A of theta and C of theta to be real functions matching these four properties, then we have that the vector of angles needed to define the axis for the rotations can be efficiently computed. That's the first thing. That this is going to link the sequence of rotations that I need with the decomposition of the whole rotation into the Pauli basis. So this can be efficiently computed. So if I try to do a transformation that has these coefficients, I know how to calculate the angles to implement the rotations. Okay, this is first thing. Second thing is, okay, the number of rotations. When I was manipulating, I had n rotations. Applied to the ancilla. Okay. This is the first important thing. The second one, it is the kind of functions that we can achieve with these two guys here. So imagine that we have picked these two guys. What kind of transformations we can obtain? And the thing is that if we pick a function that goes from minus pi to pi to minus pi to pi to be odd, then it is possible to assert that the maximum difference between this is minor than epsilon. So basically, with these A and C to be real functions, it is able to approximate these odd functions. And furthermore, we know how to compute the angles to achieve these A and C. So now we have all the ingredients here to put all of this together. Because the function that we want to implement, it is the sine of theta. And it's odd, it's defined in that range, and we have a good approximation for this. The last thing that we need to know, it is what should be the initial state for the ancilla. The initial state for the ancilla, we choose the plus state, and to project, we also choose the plus state. So now we know that the transformation that we want to apply, it is the sine up to a certain prefactor, and that prefactor is going to be limited by actually this range, so that's going to limit the simulation time that we may have because of this prefactor. And basically, if we take our state resulting from the quantum random walk, so we have applied the quantum random walk, we got a state. And this state has a phase that we want to transform. So basically, to transform the phase of this state, we add an ancilla on the plus state. And then we know that the function that we want to compute is the sine. So basically, the sine can be approximated with this A of theta and this C of theta. And to implement this A of theta and this C of theta, we have a sequence of rotations. and these rotations are defined by the axis, and the axis is defined by this vector of phi. So basically, I can efficiently find which is this vector of rotations. And basically, I can implement the quantum signal processing and then project into the plus state. So basically, in the end, I'm going to have a transformation which is going to be this one. Questions? Yeah.
So that result for all functions, it means like that for any epsilon you can find an m and a sequence of axes such that you have this inequality.
Yeah. Basically, you can say, yeah, that for a given epsilon you can have like the Fourier approximation of this function in terms of these two guys with an arbitrary precision.
But these two guys depending on being something that satisfies the previous conditions.
Yeah. Yeah, because this is a Fourier series in cosine and this is a Fourier series in sine.
Okay, so this means that for any epsilon, there are A and C satisfying that.
Yeah.
There is an N.
No,
Yeah, there is a capital N. You also need to fix like the.
You need to fix N, which then fixes A and C. Okay, you have to set it in A and C.
Yeah, basically, by choosing N, you can have an arbitrary precision here. So these are Fourier series up to k over 2, well, up to n over 2. This is a Fourier series of sum of cosines. Thing is this.
You are approximating A and C by the Fourier series until step n and a half.
Yeah.
And this is an error. And then by increasing n, you can reduce the error. Huh?
Yeah, that's it. Well, there are several things and details on like how this error propagates, but in the end, everything is efficient. I don't want to go into details. I don't know. I mean, that's a sufficient condition, but they don't really give an intuition about that.
Has this been done?
Experimentally, yeah, recently.
How this n grows?
Well, depending on the accuracy that you need.
Yeah. So how this n grows depending on the error condition.
Yeah. In the end, you give the complexity in terms of like the depth of the circuit, and basically everything is going to be related. So well, let me check. I can check it. I don't think it's a really big matter. But. And how is this n? Yeah, I have it here. Well, basically that's going to, well, we can talk later about this. But yeah, it's here. I don't want to go into these details because you need to use the Jacobi-Unger expansion and blah, 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 blah. But yeah, like you can, for now, you can just basically assume that there's like a good scaling with this. So yeah, in the end, we can follow all of this structure and do the simulation. And the overall complexity of doing the quantum random walk plus doing this transformation into the phases, it's going to scale as this, which is the most efficient known theorem to simulate sparse Hamiltonian in quantum computing. So this is the main result. And I'm going to finish with this. Yeah, basically we have D sparse Hamiltonian, and we have it's on n qubits, and the matrix elements can be described with n-bit precision. This is because oracle H. And we want to simulate for time t with success probability (1 minus 2 epsilon). So we need order
It's not for t. It's precisely t times the norm of h. It's giving you the maximum t. It's a smaller radical than pi.
But yeah, that's the parameter of time, but like that's a real simulation time that you want to calculate this. That's it, the simulation time. Well, I'm going to finish this. So that's it. No. Depends on the precision in which you encode the entries of the Hamiltonian and the number of qubits. Yeah, because basically the number of 2-qubit gates and single qubit gates that we are going to use are used for ones that you have, you need like a, what's the name? Quantum ancilla, no, yeah, but it's like the one of the HHL, quantum ancilla encoder. Yeah, so basically when you have AK and AJK, you need to translate this into the amplitude. And that's going to depend only on the accuracy on which you have encoded this and the number of qubits that you have. So that's not going to depend on the sparsity, because that's like a parallel operation. And you also need these single and 2 qubit gates for the quantum signal processing, but it's not that much. Yeah, so basically we have the validity, the range of validity for this simulation like this, because in the previous theorem I have asked for the function to be range into the interval, minus pi pi. So basically, if we go further by rescaling the sign with a prefactor, that may not be efficient. So actually, the transformation that we do, this h of theta, it's minus the norm of the Hamiltonian times sparsity times sin of theta. So we know that we can efficiently implement sine of theta, but this prefactor may result into prohibitive. So that's going to establish a validity range for the simulation time, which is this factor here. So this pseudo time is what is going to give you the range of validity. And this oracle is query complexity, not gate complexity. So if the oracle cannot efficiently implement the description of the Hamiltonian into binary approximation, this may destroy any potential advantage. So an example of this is in the case that you had like diagonal Hamiltonian. Obviously the oracle, the finder oracle, which is giving you the position of the non-zero entries, is trivial because everything is into diagonal, but then you need to describe the elements of the diagonal. And that's one of the trickiest things, because if you have like a function encoded into the diagonal that cannot be efficiently described with Boolean operations, then you may have like a prohibitive complexity of implementing this oracle. Because remember that this oracle OH is basically mapping, is a two-dimensional function that given two coordinates, j and k, is going to give you the value of that. So in case of having a diagonal Hamiltonian, this will be like one single variable function. So basically, that function is going to describe the entries into the diagonal, but this function must be efficiently implemented. So if you had, for instance, that the f of j is exponential of j, that's not that easily implementable into Boolean operators, because you need an approximation or a way to compute the exponential, which is not that easy. But yeah, one of the trickiest part here is that this is like the most efficient way to implement this, because this complexity here and this complexity here come from two different backgrounds, from the description and of the Hamiltonian and from the signal processing. Here we have the lowest possible scaling of the complexity with the sparsity and time, and the lowest possible scaling for the error, and then we have that these two errors are additive and not multiplicative. So this is like the most optimal known way of implementing, and it's proved to be the optimal one for implementing sparse Hamiltonians. So for sparse Hamiltonian cannot be better than this, and the thing is that we still need to analyze the complexity of this, which in the end is a black box. So it is not that trivial to do this, but at least this is optimal in that regard. And the fact of having an exponential advantage with respect to a classical method depends on the feasibility of building the black box of the oracle. So yeah, this has been everything, I guess. So thank you very much. Questions? No? Lunch?
You have said that they have done it experimentally.
Yeah. They have done it experimentally. You pick a trivial Hamiltonian for doing that. It is really problem dependent, and depending on the Hamiltonian, as I was saying the other day, depending on the Hamiltonian that you want to implement. But for something as like having the harmonic oscillator, which is kind of this, it's like p squared or p with finite difference may have this representation. So getting this shouldn't be that difficult, because basically you only need, you know that the function that you want to compute, but it's a complex value. So maybe you use some of the ancillary registers, m, and you can use this m over 2 to compute the real part, this m over 2 to compute the imaginary part. And then basically the oracle, the only thing that needs to do is to compare. So if k is larger than j, it's plus. If k is smaller than j, it's minus. That's what the oracle needs to do, to compare k and j. So basically something like that. So yeah, well, it depends on how you want to implement this. But this is a fault tolerant algorithm. This is not an ISK-friendly algorithm. So yeah, there's a paper in which they have recently implemented this with a toy model. More questions?
Why doesn't this work for non-slots?
Because this is not, the scaling of the complexity is not optimal, and there may be more optimal ways of implementing that kind of Hamiltonians.
If D is very big compared with information.
Yeah, in the end, you have a factor here which is the sparsity.
Yeah.
So if you have a Hamiltonian which is not, well, if this sparsity is not small enough compared to the dimension, then this is going to become exponential. And there might be alternative ways of simulating that kind of Hamiltonians. This is one of the ways.
Let's call more or less D. To consider D some of them better than other approaches.
Well, I don't know that answer. I know that this is the best technique that shows the base scaling with the sparsity. But there are other techniques that will scale with a different magnitude of the Hamiltonian. So typically there are 3 schools for simulating the Hamiltonian. One of them is sparsity. The other one is linear combination of unitaries. So basically you decompose the Hamiltonian into Pauli phase systems, and you simulate the Pauli phase systems, and you have a scaling with how many terms you may have from decomposing the Hamiltonian. And the third school is product formula decomposition. So basically you have total decomposition and all of this stuff. So all of these have different complexity scalings with different parameters. So if you compare the formulas, there must be a crossing point depending on the kind of Hamiltonian you have. I don't know. I can give you the reference and the values of every complexity, but I have not calculated. But I guess that depending what parameters you choose to represent your Hamiltonian, you may have an optimal protocol.
As a rule of thumb, when the sparsity goes as a logarithm of the size of the matrix.
I can.
As a rule of thumb,
Yeah.
it's not the rule, but when the sparsity grows with the log of the size of the matrix.
Yeah, n.
So it's n, yeah.
Yeah, could be. I have not really checked that out. I could, but yeah, that's the main idea. That for this kind of Hamiltonians that are especially of interest when representing continuous variable systems, because for continuous variable systems you are going to have position operator or momentum operator. You may have that this is a really efficient way. So now that we know that we have this, next day I can tell you about mixed semi-classical simulations and why this is useful for simulating semi-classical dynamics, especially in the case of quantum fields. So yeah, That's like the starting point for being able to explain you one of the latest works. So yeah, that's kind of relevant. Maybe like for spin Hamiltonians, where you have like k local terms and all these stuff, it's more useful to have like another descriptions for Hamiltonian simulation. But for continuous variables, it's like kind of. And let's go for it.